Okay, in this week's class, for the vast majority of it, I'm going to go through those revision questions that I gave you for homework last week. I'm sure that you found some of them very difficult, which is fine. Basically, I'm just trying to give you a couple of awkward things just to remind you of all the things we've done over the last couple of months. Once we've finished the revision sheets, the next thing we're going to look at are the 8 proofs that are on the trigonometry course. We've done 3 or 4 of them throughout the year. What I want to do now is just literally go through all 8 of them in one go so that they're all fresh in your mind. Okay, so to start off this week's class, I'm going to go through the 15 questions on the 2 revision sheets that I gave you from last week. So make sure that before you watch this, you've attempted the 15 questions. You'll have noticed that it was just lots and bits and pieces here. At this stage in the year, we always think it's important to just start revising probably some of the easier stuff that you might have forgotten. Question 1 here, you were given this fraction and you're asked to simplify. You've a plus b all over 1 over a plus 1 over b. The first thing that we should do here is, on the bottom of the fraction, try and add 1 over a and 1 over b together. So to start this one off, we'll do nothing with the top of the fraction. We'll just leave it as a over a plus b. Now, what we need to do on the bottom of the fraction is I want to get a common denominator for 1 over a plus 1 over b. To get a common denominator, we just multiply all the denominators by each other. The common denominator for 1 over a plus 1 over b is ab. It's basically just this multiplied by this. And then you have to figure out what goes on the top. To figure that out, you'd ask yourself, how many times does the bottom of the first fraction divide into the common denominator? A into AB goes b times. A would cancel out with itself and I'd be left with b. So I'd multiply b by what's on the top of that fraction. B by 1 is just b. And then I do the same thing with this one. I'd ask myself, how many times does b divide into the common denominator? B divides into AB a times. It cancels with itself and I'm just left with a. And then a multiplied by 1 is just a. Now, in algebra and any topic we're dealing with in maths, you don't want to have more than one fraction line in an expression. Here I have a plus b divided by this fraction. Dividing by this fraction is the same as multiplying by the reciprocal. So I can just rewrite this one. A plus b, instead of dividing by this entire fraction, I'm going to flip the fraction and multiply. Dividing by b plus a over ab is the same as multiplying by ab over b plus a. So I'm just flipping the fraction and multiplying. Now, so this is a plus b over 1 multiplied by ab over b plus a. Now you should notice that a plus b and that what's here and what's here are the exact same thing. A plus b will divide into a plus b once, and I'm just left with ab. So simplified fully, that one just ends up as ab. So again, a lot of the questions in this revision sheet are just practicing your manipulation and that kind of thing. Your answer to question 1 was just this. And the second question here, you were given c is equal to b squared minus ac over b plus a. And you were asked to express a in terms of the other variables. Another way of asking this question is, I could have said, make a the subject of the equation. If I had said make a the subject of the equation, it means the same thing. It means basically get a on its own. So the first thing that I decided to do was to multiply both sides by b plus a in order to eliminate the fraction. I then multiplied c by b plus a and I got bc plus ac. And at this stage, the logical thing to do, since I'm trying to isolate a, was to bring all the terms with an a to one side of the equation, all the terms without an a to the other side of the equation. When I did that, I ended up with ac plus ac equals b squared minus bc. I noticed then that this is 1ac plus 1ac. These are clearly like terms that I can add together. 1ac plus 1ac gives me 2ac. And then in order to get a on its own, I divided both sides by 2c, and I end up with a is equal to b squared minus bc over 2c. Now, a very common mistake that I see students making is when they get to this stage that they think that this c and this c will cancel out. But you're not allowed to do that. You can only divide, if there's a c on the bottom of the fraction, I could divide c into the top of the fraction, but only if I'm dividing c into every term. If there was a c in every term on the top, I could divide the c on the bottom into each one on the top. But I can't just selectively divide this c into the c in this term while ignoring that term. It doesn't make sense. So my final answer, fully simplified, is a is equal to b squared minus bc over 2c. Now question 3, I hope it was clear what we wanted you to do. Now in question 3, I hope it was clear what I wanted you to do here. I want you to do the same thing as you did in question 2. In question 2 we made A the subject of the equation. In question 3 we needed to make V the subject of the equation. So there's a couple of different ways of doing this one. What I decided to do was to get a common denominator just for the right hand side of the equation. The common denominator for 1 over u plus 1 over v is uv. And then I'd ask myself, how many times does the bottom of the first fraction divide into the common denominator? U would cancel with itself and I'm left with v. So v multiplied by the top of the fraction just gives me v. Follow the same logic and I'd end up with a u on the a plus u because of this fraction. So if I got a common denominator for the right hand side, I end up with v plus u over uv. What I decided to do then was to eliminate the fraction on the right hand side by multiplying both sides by uv. In which case I end up with no fraction on the right and I end up with a uv on the left. I then want to eliminate the fraction on the left, so I decided to multiply both sides by f, in which case the fraction on the left is gone and I'm left with vf plus uf. At this stage, the logical thing to do is to bring all the terms with the v's to one side of the equation. And I got uv minus vf equals uf. My goal here is to get v on its own, so I factorised out v and I was left with v times u minus f equals uf. In order to get v on its own, I divide both sides by the coefficient of v, which is u minus f. And your final answer in this case is that v is equal to uf divided by u minus f. In question 4, you were given minus 4 over root 5 minus 3. And you're asked to express this in the form of root 5 plus a number. Now you should recognize this from our notes when we started off trigonometry and we were introducing you to compound angle formula. We did a number of questions with this in it. And this is also very, very similar to something that comes up in complex numbers. In complex numbers, when you have an I on the bottom of a fraction, you need to be able to eliminate the I. And in algebra, when you have a surd on the bottom of a fraction, you need to be able to eliminate the surd. Now, if you just plug this into your calculator would straight away tell you that it becomes root 5 plus 3. However, in an exam question, they could easily ask you to show that this is equal to root 5 plus 3. You'd have to derive it for yourself. So the problem with the question you were given is that there's a surd on the bottom of the fraction. In order to eliminate the surd, you have to figure out what do you need to multiply root 5 minus 3 by in order to eliminate the surd. If you multiply root 5 minus 3 by the conjugate of root 5 minus 3, then the middle terms will cancel each other out and you'll be left with no more surds. The conjugate of root 5 minus 3, you change the sign in front of the surd, you multiply by minus root 5 minus 3. So all I've done is the exact same thing again, except I've changed the sign in front of the surd. I want you to be aware there that, in fact, if you had actually just changed the sign in front of the 3 and you multiply them out, they would cancel each other out. You'd end up with the same answer either way. But I always tell you, and as we went through in class earlier in the year, I think it's just a safer bet, you change the sign in front of your surd. So if I multiply root 5 minus 3 by minus root 5 minus 3, when I multiply out the double brackets, the middle terms will cancel and I'll have no more surds. And that's obviously my goal. However, I can't just randomly multiply the bottom of an expression by minus root 5 minus 3. In order to compensate for it, I have to also multiply the top by minus root 5 minus 3. Because then ultimately I'm multiplying by the same thing on the top and the bottom, which means I'm multiplying the expression by 1. So I'm not changing the value of the expression. So all I have to do now is multiply it out. Minus 4 by minus root 5 minus 3. Well, minus 4 by minus root 5 gives me plus 4 root 5. Minus 4 by minus 3 gives me plus 12. But it's the bottom of the fraction that I want to hone in on. Root 5 by minus root 5 gives me minus 5. Root 5 by minus 3 gives me minus 3 root 5. Minus 3 by minus root 5 gives me plus 3 root 5. And minus 3 by minus 3 gives me plus 9. When you multiply something by its conjugate, the middle terms will always cancel each other out. This is very, very similar to what happens in complex numbers when you're trying to get rid of an I. If you multiply a complex number by its conjugate, then the middle terms cancel out and you're left with just a number. Ultimately, the middle terms cancel and I'm left with 9 minus 5, which is 4. 4 into 4 goes once, so I end up with 1 root 5. 4 into 12 goes 3 times, so I end up with 3. So your final answer there is just root 5 plus 3. Okay, so question 5 here, again, it's just a mix of different things you could get in algebra. The first one here was 1 over x plus 1 plus 4 over 2x minus 1 equals 5 over 3. We've got one equation and one unknown, which means we can solve this to find the value of x. Now you have a few different options here. You could get a common denominator for the left-hand side and then turn this into one fraction and then just multiply across and eliminate your fractions. But that's the method that I followed for the second question, the third question, which was 1 over f equals 1 over u plus 1 over v. When we had three fractions that time, I decided to get a common denominator for just one side of the equation. So I want to do this one slightly differently. The other option when you have three fractions and an equals is you can just get a common denominator for all three. The common denominator for these fractions is x plus 1 times 2x minus 1 times 3. You literally just list them along the bottom. To work out what goes on the top, you take the bottom of the first fraction and you figure out how many times would x plus 1 divide into the common denominator. If I divided x plus 1 into the common denominator, it would cancel with itself and I'd be left with 2x minus 1 and 3. So it's the top of the fraction by 2x minus 1 times 3. It's just this by basically the other denominators. Then I continue on and I ask myself how many times will the bottom of this fraction divide into the common denominator. The 2x minus 1 would cancel with itself and I just end up multiplying 4 by x plus 1 by 3. I follow the same logic again. There's an equals between the next terms and then it's 5 times 2x minus 1 times x plus 1. Now if you have a fraction with an equals on the top, you can just ignore your denominator. The whole point of getting a common denominator when there's an equals there is to eliminate the fraction. Because there's an equals on the top of the fraction, I can just eliminate the denominator. And then we just need to multiply it out. Now obviously I skipped a couple of lines here, but when you multiply it out, you should end up with the quadratic equation 10x squared minus 13x minus 14. You can factorize this and you get 10x plus 7 times x minus 2. And when you solve that, your two possible answers for x are x equals minus 7 over 10 or x equals 2. In part B here, we were given the absolute value of 3x minus 2 equals 4. Remember that in order to eliminate absolute value signs, you can square both sides or you can take it as a plus or a minus. In a question like this, as far as I'm concerned, the easiest thing to do is to square both sides. If you square 3x minus 2, you can ensure that whatever you have is positive. So you square the left hand side and you square the right hand side. 4 squared works out as 16. And if you multiply 3x minus 2 by 3x minus 2, you're going to end up with 4x squared minus 12x plus 4. At this stage, you should have recognized you have an x squared, an x and a number. So you need to subtract 16 from both sides so that you've got everything on one side of the equation and you can factorize your quadratic equation. You end up with 9x squared minus 12x minus 12. Now you could have factorized it at this stage, but it's easier to divide everything by 3. And if you divide everything by 3 at this stage, you get 3x squared minus 4x minus 4. The factors of that quadratic equation are 3x plus 2 times x minus 2. You can then let each of those factors equal to 0 and solve it. And the two answers here work out as x is equal to minus 2/3 or x is equal to 2. In part C here, we were given x is equal to the square root of 3x plus 7 minus 1. Obviously, the complication in this equation is the presence of the surd. So I need to eliminate the surd. And in order to eliminate the surd, I need to square it. However, I can't square it at this stage. If you decided to square both sides at this stage, you have to square each side of the equation together. So the left-hand side would obviously just become x squared, but the right-hand side, you would have to multiply this out as double brackets. It'd be like multiplying out that bracket by itself. And in that case, you're not going to eliminate the surds. So in the form the equation was given to you is no good. You need to manipulate it. What you need to do is add 1 to both sides so that you've isolated the term with the surd in it. And once you add 1 to both sides, now you want to square both sides. It's easy enough to square x plus 1, to multiply x plus 1 by itself. And when you square the right hand side, the surd and the squared cancel each other out. X plus 1 by x plus 1 is x squared plus 2x plus 1. And in this case, the squared and the surd cancel out, and I'm left with 3x plus 7. What you should do next is bring all your terms to the left-hand side, and you end up with x squared minus x minus 6. If you factorize that quadratic, you get x minus 3 times x plus 2. And when you solve this, your answers are x equals 3 and x equals minus 2. However, in a question where there was a surd at the start, what you need to do whenever you get your values is you need to sub these values into the original line to verify that it's accurate. So because the variable was in a surd in the original equation, I need to verify or double check if my answers are correct. So if you sub in x equals 3, in that case, if you sub in x equals 3 into the original line, it makes sense. You end up with 3 equals 3, so it's true. So I'm happy enough with my answer x equals 3. On the other hand, if you sub in x equals minus 2, the other answer, in this case you end up with minus 2 equals 0, and clearly they're two different numbers, so they're not equal to each other. So we actually had to eliminate the value x equals minus 2. So just be careful there. If there's a surd in the original equation, if the variable is in the surd, you have to verify your answers, because it tends to be the case that one of them is true and the other one isn't. Now as well, another piece of advice is, I know a lot of students, when they verify one is true, they don't bother subbing in the other one. Even though this one was true, I still went ahead and subbed in the other one to double check. So you should sub in both of your answers into the question to see which ones are true or false. In part D, we had 2 times the absolute value of x plus 1 minus the absolute value of x plus 3. Once again, in order to eliminate our absolute value signs, what we want to do here is we want to square both sides. However, we don't want to square both sides at this stage, because if you multiplied out the left hand side, that would be an absolute nightmare. It's going to be really, really tricky, because you have to multiply out, you'd have to multiply this out as double brackets. What you want to do first is move one of the terms to the right hand side. So I added the absolute value of x plus 3 to both sides, and I got to this stage. And it's far easier at this stage. What I decided to do now was to square both sides, because if I squared everything, then the absolute value signs would be gone. So the left hand side became 2 times x plus 1, and it's all of that to be squared, and the right hand side just becomes x plus 3 to be squared. If I square it out, I can ignore the absolute value signs. 2 by 2 is 4, and x plus 1 squared gives me x squared plus 2x plus 1. And x plus 3 squared is x squared plus 6x plus 9. I then multiplied 4 by the left hand side, and I moved all my terms to the left hand side and got the quadratic 3x squared plus 2x minus 5. If we factorize and solve this one, your two answers for x were x equals minus 5 over 3, or else x equals 1. Okay, in the last part of question 5, you were given the cubic 4x cubed plus 10x squared minus 7x minus 3, and you're asked to solve it. If you're asked to solve a cubic and you're given none of the roots, the first thing you have to do is just use trial and error to find the first root. So logically, you'd start off by investigating 1. 1 is the most logical one to start with. So you sub in 1 and investigate if when you sub in 1 is the whole thing equal to 0. In this case, when I subbed in 1, I ended up with 4 is equal to 0. Obviously, it's not equal to 0, so that told me that x equals 1 was not a root. If plus 1 doesn't work, then you try minus 1. And that didn't work, so then you try 2, and that didn't work, so you try minus 2, you try 3, and then eventually you would have tried minus 3. And when you try minus 3, everything cancels out and you're left with 0 equals 0. So that tells you that x equals minus 3 is a root. If you know that x equals minus 3 is a root, you can convert that to a factor by adding 3 to both sides. If x equals minus 3 is a root, then x plus 3 equals 0 is one of the factors. And if you know one of the factors, I can now divide x plus 3 into the original cubic, and I'll get a quadratic on the top. And when I factorize that quadratic, it will give me the other two roots of this cubic. So once we have a factor, you divide your factor into the original cubic. Using long division here, we end up realizing that the other factor was 4x squared minus 2x minus 1. Usually what we would do then is we'd factorize that, and if you factorize this quadratic, you would get the other two answers. However, we're not going to be able to, obviously this one is awkward roots, so we're not going to be able to find factors for this one. So we need to use the minus b formula to solve this cubic and to solve this quadratic and find the other two roots of the cubic. So the minus b formula is relatively straightforward. In this case, our a would be 4, our b would be minus 2, and our c is minus 1. And when you use the minus b formula, you end up with x equals 0.81 or x equals minus 0.31. And ultimately the question was to solve this cubic, which means you should write out the three roots beside each other. The root we worked out at the very start was x equals minus 3. So the very last thing you should do in a question like this is you write out the three roots of your cubic. Okay, part F, question 5, part F. Most of you are probably confident enough with it, but these are marked very, very difficult. So I want to really hone in, make sure you're getting the very last few lines of this one correct. If you have 3x plus 1 over x minus 1 is greater than or equal to 2, what you need to do is multiply both sides by the denominator to be squared. In other words, multiply both sides by x minus 1 to be squared. And then on the left hand side, x minus 1 in the bottom will divide into one of the x minus 1's on top, and your squared is gone. If you multiply 3x plus 1 by x minus 1, you'll get 3x minus 2x minus 1. And if you multiply 2 by x minus 1 to be squared, you end up with 2x squared minus 4x plus 2. You move everything to one side, and you get to this stage where you've got a quadratic. I'm saying x squared plus 2x minus 3 is greater than or equal to 0. Now, it's from here that I want to focus on. Now you're going to ignore the inequality, and you're going to make that an equals. And from here on, we're going to now factorize and solve this quadratic so that we can sketch a curve. In order to answer the question that this line asks, we have to sketch our curve. If you have an inequality and a variable to be squared, you should always do this. I'm letting it equal to 0, and I worked out that the factors were x plus 3 times x minus 1, which means if I solve it, I get x equals minus 3 and x equals 1. Now, even though it says in the question that x can't be equal to 1, I've no problem with this for the moment. This is not my answer. The only reason I've done this is because that will allow me to sketch a rough graph of what this quadratic looks like. I know that this quadratic crosses the x-axis at minus 3 and the x-axis at 1. There's a plus in front of the x squared, so it's a U-shape. So if I was to sketch this graph, it would look roughly like this, where I marked in minus 3 on my x-axis and I marked in 1 on my x-axis. Then you go back to the last line you had an inequality. On this line it says, when is the quadratic greater than or equal to 0? The quadratic is greater than 0 when it's above the x-axis. So that refers to this region and it refers to this region. That's two separate regions, which means I have to give two separate answers. For the first one, it's when x values are to the left of minus 3. Or in other words, when x is less than or equal to minus 3. And the second one is when x values are bigger than 1 or to the right of 1, and it's when x is greater than 1. Notice that we don't put in the equal to there because x cannot be equal to 1. And the reason x can't be equal to 1 is because if x was equal to 1, the bottom of this fraction would be 0. And we cannot have a 0 on the bottom of a fraction. So in that case, you don't put in the equal to 1 there. That's where the fact that x equals 1 comes into play. It's that you don't put in the equal to sign at the end. And in the vast majority of the questions that come up in this form, you have to eliminate the equals on one of your answers at the end. Okay, now in question 6, we were asked to prove that a over b squared plus b over a squared is greater than or equal to 1 over a plus 1 over b. You needed to recognize this as an abstract inequality. This is one of the questions where you're going to bring everything to one side and you're going to end up with everything to be squared. So that you can say that this has to be positive because any real number to be squared is greater than or equal to 0. It's a few months since we've looked at any of these. In this question, it should have specified that a and b are elements of OR. It should have specified we can only do these questions if a and b are real numbers. In this case, the easiest thing to do was to get a common denominator for all four of your fractions. What will b squared, a, and b all divide into? The term that they will all divide into is a squared, b squared. This term divides into a squared, b squared. A squared divides into it, a divides into it, and b divides into it. So they all divide into a squared, b squared. Now I'm going to ask myself, how many times does b squared divide into the common denominator? B squared will cancel with itself and I'm left with a squared. So it'll be a squared multiplied by what's on the top, which is a squared by a gives me a cubed. Then I ask myself how many times a squared will divide into the common denominator. So I cancel the a squared and I'm left with b squared. B squared multiplied by what's on the top will be b cubed. Then I have a greater than or equal to sign, and I ask myself, how many times will a divide into this? Well, if I divided a into a squared, b squared, the a would cancel with one of the a's, and I would be left with a b squared. And then I'd say, how many times does b divide into a squared, b squared? B divides into a squared, b squared, and cancels with one of the b's, and I'm left with just a squared b. Multiply that by the top and I just get a squared b. So that's a common denominator. And we came across this already. If you have a fraction with an equals on the top or an inequality on the top, you can just ignore the bottom of the fraction. So I can just eliminate that, and now at least I've got something that's linear. Now, if you knew that this was an abstract inequality, you would know that eventually I need to bring everything to one side. In fact, bring everything to one side and end up with the whole thing to be squared. However, in this case, what we should do first is factorize the left-hand side. This is the sum of two cubes. You should remember your sum of two cubes. If you factorize a cubed plus b cubed, you get a plus b times a squared minus ab plus b squared. And I could say that that's greater than or equal to the right-hand side. On the right-hand side, I can also factorize. On the right-hand side, what's common to both terms is the term ab. So I can factorize out ab, because ab is in both terms. ab into ab squared goes b times. ab into a squared b goes a times. The reason that this is handy, because I've got a plus b here and I've got an a plus b here. I could just divide both sides by a plus b and these would cancel each other out. And I'm just left with a squared minus ab plus b squared is greater than or equal to ab. Now, in these questions, it was always inevitable that we were going to have to bring everything to one side. It's at this stage that I'm going to bring everything to one side. So I'm going to subtract ab from both sides. If I subtract ab from both sides, I'm just left with a squared minus ab plus b squared is greater than or equal to 0. Clearly the two middle terms there are like terms. Minus ab gives me minus 2ab. Now you should recognize this. A squared minus 2ab plus b squared, you should recognize that as a minus b to be squared. When we were doing abstract inequalities, that was one of the things that I said you just need to learn. You just need to recognize that a squared minus 2ab plus b squared is the same as a minus b to be squared. And now I am happy out. That's the end of the maths. I can say that this one is true. That's definitely true. The reason I know it's true is because any real number to be squared is always greater than or equal to 0. Even if the thing that was in this bracket was a minus, if I multiplied it by itself, it would become a positive. It only applies if it's for a real number, so that's why the question needs to say that a and b are elements of OR. Okay, if we have a look at question 7 here. In question 7, we had two equations and two unknowns, so we had a simultaneous equation. There are two different ways you can do simultaneous equations at Leaving Cert level. You can do them the same way as you did at Junior Cert, or you can do them by substitution. If you want to do them by substitution, I could have taken one of the equations and isolated x or isolated y and subbed it into the other one. But it's easier to follow the Junior Cert method. It's easier to just try and make it look the way that they looked at Junior Cert level. So what I decided to do was to just take each of my equations and try to eliminate the fractions. Since the first equation, the first fraction is over 3 and the last term is over 5, I realised that if I multiply the entire line by 15, that will eliminate the fractions. So if I multiply 2x minus 5 over 3 by 15, 3 divides into 15 5 times. So I have to multiply the top of the fraction by 5. 2x by 5 is 10x, minus 5 by 5 is minus 25. And then 6 by 15 gave me 90, and 5 divides into 15 3 times. So I have to multiply the top of that fraction by 3, so it becomes minus 3y. If I look at the second equation, the first term is over 10 and the last term is over 2. 2 and 10 both divide into 10. So if I multiply the entire line by 10, I'll manage to eliminate the fraction. So in the first one, 3x over 10 by 10 is just 3x. 2 by 10 is 20. And 2 divides into 10 5 times, so it's 5 times what's on the top of the fraction. 5 by 3y is 15y. 5 by minus 5 is minus 25. Now this is a basic enough question. I just decided to bring all my x's and y's to the left and numbers to the right. I ended up with 3y plus 10x equals 115 and minus 15y plus 3x equals minus 45. I then noticed that the easiest variable to eliminate is the y's. If there's a minus 15y in the bottom of in the second term, I want a plus 15y on the top in the first equation. So I decided to multiply the first line by 5. 3y by 5 is 15y, 10x by 5 is 50x, 115 by 5 is 575. Now it's from here, it's very straightforward. I'm just going to finish this one up at the top of the page. So it's really straightforward from here. I have plus 15y and minus 15y in each case, so they cancel each other out. 50 and 3 gives me 53x. 575 minus 45 gives me 530. So to get x on its own, I just divide both sides by 53 and I end up with x equals 10. Once I have a value for x, I can sub back into either of my original equations and find the corresponding value for y. I subbed into the top of the equation and I ended up with y equals 5. So your answer there is x equals 10 and y equals 5. Okay, there was a typo on question 8 that I forgot to change. So what I want you to do is take this one down. In the notes, I think that was actually an equals. It should have been a plus. So this one, you have 2 to the power of 2x plus 1 minus 5 times 2 to the power of x plus 2 equals 0. So I want you to take that one down now, and I want you to pause the video and try and work through it before you watch my solution. In this question, we clearly need to use substitution. You need to recognize that this is actually a quadratic equation. And the problem at the moment is that there's an unknown in the power. But usually if there's an unknown in the power, that means introduce logs. But I have 3 separate terms here. Introducing logs is not feasible. What I need to do is use substitution. So I'm going to take this simple term that has an unknown in the power. Clearly the 2 to the power of x is simpler than the 2 to the power of 2x plus 1. So this is the simple one. This is going to be my substitution. Instead of 2 to the power of x, I'm going to sub in a y. That tells me that if I subbed in y, this term would just become minus 5 times y, and the last term would just be a plus 2. The problem lies in what am I going to do with the first term. So I need to try and simplify 2 to the power of 2x plus 1 so that I can get it in terms of y based on this substitution. And for that, it's relatively straightforward. A lot of students try to skip these lines, but I want you to drag these ones out. If you have 2 to the power of 2x plus 1, we can split that up. 2x is the same as 1x plus 1x. So 2 to the power of 2x plus 1 is the same as 2 to the power of x plus 1. Now I can use the first rule of powers on page 21 in my maths tables to simplify this. I can simplify this down to 2 to the power of x multiplied by 2 to the power of x multiplied by 2 to the power of 1. I know that now I've simplified it down to 2 to the power of x, now I'm happy out. Everywhere there's a 2 to the power of x, I can just sub in a y. Instead of this, I can put in y. Instead of the second bit, I can put in y. And 2 to the power of 1 is just 2. So I've simplified down the first term to y times 2. Or in other words, that's obviously just 2y squared. Now I've just got a basic quadratic. I can factorize and solve for y. And once I've solved for y, I'll sub back in and I'll be able to solve for x. So when I factorize this, I get 2y minus 1 times 1y minus 2. And when you solve your values for y there, you get y equals a half and y equals 2. However, that's not your answer because there was no y in the original equation. Like we just made y up as a substitution earlier in the question. So it's no good to just get y. You need to now get the value of x. If y is equal to a half and y is equal to 2 to the power of x, I can say that 2 to the power of x equals a half. Likewise, I can say that 2 to the power of x equals 2 to the power of 1. Now usually if the unknown is in the power, we would introduce logs. However, we can do this one in our head. A half is 1 over 2 to the power of 1. And if you look at the fifth rule of powers in your maths tables, it tells you that if you've 1 over a to the power of p, you can just bring a to the power of p up and change the sign. So 1 over 2 to the power of 1 is the same as 2 to the power of minus 1. So I can say that 2 to the power of x equals 2 to the power of minus 1. The 2's will cancel and I'm left with x equals minus 1. On the other hand, if 2 to the power of x equals 2 to the power of 1, the 2's just cancel and you're left with x equals 1. So your two answers in that case are x equals minus 1 and x equals 1. Okay, in question 9 we had a simultaneous equation. We've 2 to the power of x equals 8 to the power of y plus 1. And we've 3 to the power of x minus 9 equals 9 to the power of y. We've two equations and two unknowns, which means we can solve for x and y. But obviously the problem is that there's powers involved here. And for my first goal needs to be to eliminate the powers. Let's take the first equation. If I have 2 to the power of something on the left, I want to have a 2 to the power of something on the right. So let's just have a look at it first. On the left hand side, I'm happy enough, I'll leave that as 2 to the power of x. On the right hand side, if I have 8 to the power of something, I want to rewrite that as 2 to the power of something. If I use trial and error on my calculator, I'll deduce that 8 is the same as 2 to the power of 3. So that means that 8 to the power of y plus 1 is the same as 2 to the power of 3 to the power of y plus 1. So all I've done there is, instead of an 8, I've substituted in 2 cubed, which is the same thing. If I simplify that one down, the left-hand side will stay as it is. And if you look at the third rule of powers in your maths tables, it tells you that if you have powers in this form, you can just multiply them by each other. I just need to multiply 3 by y plus 1. And the right-hand side will become 2 to the power of 3y plus 3. And that's really useful at this stage, because now I've got 2 to the power of something on the left and 2 to the power of something on the right. The 2's will cancel, so I clearly just have x is equal to 3y plus 3. So that's straightforward enough. That's one of my, I'm going to do a simultaneous equation with this in a moment. I just need to do something similar on the right hand side. Clearly on the right hand side here, I want to get both of these as 3 to the power of something. I'll leave the left hand side exactly as it is. I'll leave it as 3 to the power of x minus 9. And instead of a 9, I need to have that as 3 to the power of something. I'm sure you're all clear that 9 is the same as 3 squared. 3 multiplied by 3 is 9. Which tells me that 9 to the power of y is the same as 3 to the power of 2 all to the power of y. Once again, I'll use the third rule of powers on page 21 in my maths tables. On the right hand side, I'll just multiply 2 by y. That just becomes 3 to the power of 2y. And the left hand side is 3 to the power of x minus 9. Now I'm happy out. 3 to the power of something on the left, 3 to the power of something on the right. The 3's will cancel, and I'm just left with x minus 9 equals 2y. Now I've got a really simple simultaneous equation that I'm going to be able to solve. So the two equations I got were x equals 3y plus 3 and x minus 9 equals 2y. I rewrote them so that the x's and y's were on the left and the numbers were on the right. I solved the two simultaneous equations and I end up with y equals 6 and x is equal to 21. Okay, in question 10, we were given the general formula un is equal to 2 times 3 to the power of n minus 5 times 2 to the power of n. We were asked to write out the first 4 terms. So straightforward enough. To get u1, you just sub in 1 everywhere there's an n, and I ended up with u1 equals minus 4. To get u2, you just sub in 2 everywhere there's an n, I ended up with u2 equals minus 2. To get u3, you just sub in 3, and u3 works out as 14. To get u4 works out as 82. Part 2 then was really straightforward. Once you've done part 1, part 2 is really straightforward. We were asked to verify that u3 minus 5 times u2 plus 6 times u1 equals 0. We worked out in the previous part of the question that u3 is 14, u2 is minus 2, and u1 is minus 4. Ultimately, you end up with 14 plus 10 minus 24. You end up with 0 equals 0, which clearly is true. So you've verified that the statement they've given you is true. Now, part 3 and 4 of question 10 were the important ones, and this is the way it's likely to come up. We know un is 2 times 3 to the power of n minus 5 times 2 to the power of n. We've been asked to get un plus 1 and un plus 2. That means everywhere there's an n, you sub in n plus 1. For example here, 3 to the power of n plus 1 can be rewritten as 3 to the power of n times 3 to the power of 1. Now, I know that a lot of students tend to make mistakes here. If you have a 3 to the power of an unknown, it is bad news. You do not multiply anything by that 3. 3 to the power of an unknown, you have to just leave it as it is. However, what I can do is multiply the 2 by the 3 to the power of 1. 2 by 3 to the power of 1 becomes 6. So that term simplified fully is just 6 times 3 to the power of n. The same thing applies over here. 2 to the power of n plus 1 becomes 2 to the power of n times 2 to the power of 1. You cannot multiply anything by the 2 to the power of n. It is bad news. You just leave it be. But minus 5 by 2 to the power of 1 is minus 10. So this becomes minus 10 times 2 to the power of n. And that's un plus 1 simplified fully. We do basically the exact same thing with un plus 2. It's just that obviously we have 2's instead of 1's. And you end up with un plus 2 simplified fully as 18 times 3 to the power of n minus 20 times 2 to the power of n. Okay, in part 4, we have to use the fact that we now know un is 2 times 3 to the power of n minus 5 times 2 to the power of n. We've simplified un plus 1 and we've simplified un plus 2. These are the three things that we need to use to answer part 4. In part 4, we've been asked to investigate if un plus 2 minus 5 times un plus 1 plus 6 times un equals 0. Instead of un plus 2, I can sub in 18 times 3 to the power of n minus 20 times 2 to the power of n. And then it's minus 5 times what we simplified for un plus 1, which I plugged in here, plus 6 times un, which is 6 times what was given in the original question. Now, once again, the things with the unknowns and the powers cannot be multiplied. You have to leave them as 3 to the power of n's and 2 to the power of n's. But what I can do, for example, with this is minus 5 by 6 gives me minus 30 times 3 to the power of n. Minus 5 times minus 10 becomes plus 50 times 2 to the power of n. Here I can multiply 6 by 2 and get 12 times 3 to the power of n. 6 by minus 5 becomes minus 30 times 2 to the power of n. On this line, we have a load of like terms. We have some terms that have 3 to the power of n's in them, some terms that have 2 to the power of n's in them. So all I've done then is I've grouped them. We had 18 times 3 to the power of n minus 30 times 3 to the power of n plus 12 times 3 to the power of n. Let's just focus on those three terms first of all. Plus 18 plus 12 is plus 30, minus 30 is 0. So all the 3 to the power of n's cancel each other out. The last three terms are minus 20 times 2 to the power of n, plus 50 times 2 to the power of n, minus 30 times 2 to the power of n. Minus 20 and minus 30 give me minus 50, plus 50. They cancel each other out again and I'm left with 0. So everything cancels out and you end up with 0 equals 0. So the statement that they give you is in fact true. Okay, in question 11 here, we were going back to complex numbers, which we haven't looked at in a long time. You were told that z to the power of 4 equals minus 8 root 3i. And you were asked to find the values of z. If you know z to the power of 4, then clearly to work out what z is, it's going to be you get the fourth root of both sides. So if I get the fourth root of the left-hand side, I'm just left with z. And I could say it's the right-hand side to the power of a quarter. Now, you should realise that if you have a complex number to the power of a power, then obviously what I need to do here is use de Moivre's theorem. But before I can use de Moivre's theorem, I need to write this complex number in polar form. So that's the first thing that we need to address. Okay, so we were given the complex number in rectangular form, which is the form a plus bi. Remember that polar form is when you write a complex number in the form of or times the cos of theta plus I times the sine of theta. So in this case, it's relatively straightforward to get your or, and it's always a bit trickier to get your theta. Or represents the modulus, and the modulus can be calculated as the square root of a squared plus b squared, where in this case a is minus 8 and b is minus 8 root 3. So or in this case would just be the square root of minus 8 to be squared plus minus 8 root 3 to be squared, which if you plug into your calculator you get 16. So straight away I know that or the modulus of the complex number is 16. The other thing I need to do is I need to work out theta, the argument. And this is where things get a bit trickier. The other thing I need to do is work out theta, the argument. And this is where things get a little bit trickier. In order to work out the argument, we need to sketch an argand diagram. Again, it just needs to be a rough sketch. It doesn't need to be accurate. The horizontal line here represents the real axis and the vertical line here represents the imaginary axis. And I know that the real value is minus 8, which I could say is roughly out here. And the imaginary value is minus 8 root 3, which might be down here. So if I was to plot the complex number minus 8 root 3, it's probably roughly out there. Now, what I need to do now is form a right angle triangle. I form a right angle triangle by joining the complex number straight up to the horizontal line, and then joining the complex number to the origin. What I'm concerned with at the moment is I want to work out the angle A, the angle that the complex number makes with the horizontal line. And in order to do that, I can just use basic junior cert trigonometry. If I know that this is minus 8 root 3, that means that the distance from the horizontal line to this point is 8 root 3. Remember, distances can't be negative, so I ignore the fact that it's a minus and just take the absolute value of this. So I know that that distance is 8 root 3, and if this is a minus 8, then clearly that implies that the distance from the vertical line to this point is 8. So if you look at our right angle triangle, I'm looking for the angle A, I know the opposite and I know the adjacent. If I know the opposite and the adjacent, I can use the tan of the angle. In a right angle triangle, the tan of the angle is the opposite over the adjacent. In this scenario, the opposite is 8 root 3, while the adjacent is 8. Now 8 will divide into 8 once, so I actually just have tan A equals root 3. Now you could use your calculator or you could use your log tables to deduce what A is, if the tan of A is the square root of 3. The question hasn't specified whether this needs to be in degrees or in radians, so in this case I'm going to do it in degrees. If you get tan inverse of the square root of 3, or if you go to page 13 in your maths tables to tan A, work your way across to root 3 and work your way up, you'll deduce that A in this case must be 60 degrees. So the angle that this complex number makes with the horizontal line is 60 degrees. However, that is not the angle that I'm looking for. I'm looking for theta, the angle that the complex number makes with the positive sense of the x-axis. The positive sense of the real axis. The positive sense of the real axis is the right-hand side of the horizontal line. So the angle I'm looking for is this angle. That entire angle is theta. But obviously, in order to work out what theta was, I needed to first work out that this is 60 degrees. I want you to just think of your trigonometry here, of your unit circle. To get a value in the third quadrant, the way we always get values in the third quadrant is we think of it as it's 180 degrees plus my reference angle, which is 60 degrees. 180 plus 60 is 240. So I know that theta, the argument for this complex number, is 240. So I've worked out the modulus and theta, the argument, so I can now say that minus 8 root 3i can actually be written as 16 times the cos of 240 plus I times the sine of 240. And in this question, I need to get all of this to the power of a quarter. So once I need to get this to the power of a quarter, I can start thinking along the lines of de Moivre's theorem, and I can figure out how I'm going to get all of my answers. Now at this stage, you should remember that if you're looking for something to the power of a fraction, anything to the power of a fraction has more than one possible answer. If it's to the power of a quarter, it's the denominator that tells me how many answers there could be. Because the denominator is a 4, there are 4 possible values for z here. And I've been asked to work out them all, so I need to get 4 different answers. So if I applied de Moivre's theorem now, I would only get one answer. So now I need to do something to ensure that I get more than one answer. And in order to think about this one, we did this in complex numbers, but we also did it in the unit circle. What we need to do, because the power is a fraction, because I want more than one answer, we need to generalize our angle. So instead of thinking of our angle as 240, we're going to call our angle 240 plus 360n. This comes up in complex numbers and in trigonometry. So if we generalize our angle, it allows us to get more than one answer. And I know that I want more than one answer because the power is a fraction. So I want it's 16 times all of this, and I want to get all of this to the power of a quarter. Now, de Moivre's theorem is available on page 20 in your maths tables, but to be honest, once you've used it once or twice, you probably already remember how to do it. The first thing I need to do is get the modulus to the power. So 16 to the power of 1/4 is 2. And then in order to get the cos of the angle plus I times the sine of the angle to the power of a quarter, you just multiply the angle by the power. So I'm just going to multiply the angle by a quarter. Multiplying by a quarter is the same as dividing by 4. So 240 multiplied by a quarter gives me 60. 360n multiplied by a quarter gives me 90n. So if I apply de Moivre's theorem, 16 becomes 16 to the power of a quarter, which is 2, and you multiply the angle by a quarter and you get this. So I can just tidy this one up, and I'm left with 60 plus 90n as both of my angles. Now, at this stage, I can now start to get my answers. I need to get 4 separate answers. I know I need 4 separate answers because the denominator of the power is a 4. In order to get 4 separate answers, I need to sub in 4 consecutive values for n. You could sub in 10, 11, 12 and 13. You could sub in any of them. But obviously the most logical values to sub in are n equals 0, n equals 1, n equals 2 and n equals 3. We're going to sub in each of these values for n, and then we're going to multiply it out, and we're going to get 4 answers in rectangular form. Okay, so I've only managed to fit 3 of the answers in here, but we'll do the next one on the next slide. I subbed in n equals 0, and if n is equal to 0, then 60 plus 90 times 0 is just 60. So I end up with 2 cos 60 plus I sine 60, which if I plug in cos 60, I get a half, sine 60 is root 3 over 2. If you multiply that by 2, you end up with 1 plus root 3i. When I subbed in n equals 1, I ended up with minus root 3 plus 1i. And when I subbed in n equals 2, I ended up with minus 1 minus root 3i. Now I'm just going to sub in n equals 3 and get my fourth answer. So to finish this one off, we just need to get our fourth answer by subbing in n equals 3. If I sub in n equals 3, obviously 90 times 3 is 270, plus 60 is 330. And if I simplify it down, I end up with root 3 minus 1i as my fourth answer for this one. Question 12 here, we were just dealing with an obscure symbol. This capital sigma means the sum of. We've come across this when we were doing series, especially when we were doing series in induction questions. You're looking for the sum of the function 3 over 10 times a half to the power of n minus 1 from or equals 3 to or equals 6. That means that you sub in 3 instead of your n, and then you sub in 4, and then you sub in 5, and then you sub in 6. You sub in all the numbers from this one to this one, and you add them all together. So I subbed in 3, then I plus between them subbed in 4, plus between them subbed in 5, plus between them subbed in 6. You can just individually plug each of these into your calculator. You get 3 over 40, 3 over 80, 3 over 160, and 3 over 320. And if you add them all together, you get 9 over 64. So just remember that that symbol, it means the sum of. And you sub in values from the number on the bottom until you get to the number on the top. Very similar to what we would have done in induction earlier on in the year. Okay, in question 13, we were told that un was equal to n minus 20 times 2 to the power of n. And we were asked to verify an expression or an equation that has un in it, un plus 1 and un plus 2. So before you even worry about the equation, you should first work out un plus 1 and then work out un plus 2. It's relatively straightforward to do so. What I did for un plus 1, everywhere there's an n, I just subbed in n plus 1. So I ended up with n plus 1 here and an n plus 1 in my power. N plus 1 minus 20 is n minus 19, and 2 to the power of n plus 1 is the same as 2 to the power of n times 2 to the power of 1. Again, a 2 to the power of an unknown is bad news and I don't want to go near it. But I can multiply 2 by n and get 2n, 2 by minus 19 and get minus 38. So un plus 1 simplified fully is 2n minus 38 times 2 to the power of n. Now I need to work out what un plus 2 is. To work out un plus 2, everywhere there's an n, I'm going to sub in n plus 2. So it becomes n plus 2 minus 20, which is n minus 18. And instead of 2 to the power of n, it becomes 2 to the power of n plus 2, which is the same as 2 to the power of n times 2 to the power of 2. 2 to the power of 2 is 4. If I multiply 4 by n, I get 4n. 4 by minus 18, I get minus 72. So un plus 2 simplified fully is 4n minus 72 times 2 to the power of n. Now that I have un plus 2, un plus 1, and un, I can investigate what I've been asked to verify. So now that I know un plus 1, and un plus 2, I'm ready to investigate if un plus 2 minus 4 times un plus 1 plus 4 times un equals 0. All I did here was I subbed in. Instead of un plus 2, I subbed in what I had worked out. Instead of un plus 1, I subbed this in. And instead of un, I subbed in this. At this stage, every term has a 2 to the power of n in it. So what I can do is just divide everything by 2 to the power of n, and all my 2 to the power of n's are gone. And then I'm happy out because there's no more unknown in the power. Now it's just basic algebra. You just multiply everything out. Minus 4 by 2n is minus 8n. Minus 4 by minus 38 is plus 152. 4 by n is 4n, and 4 by minus 20 is minus 80. And at that stage I just grouped all my n's. I got 8n minus 8n. Grouped all my numbers, I got 52 minus 52. So obviously everything cancels out and I'm left with 0 equals 0. In the second part of this question, it asked me for what values of n, which is greater than or equal to 0, is un plus 1 greater than 3 times un. In order to answer this question, I need to incorporate the fact that I know un plus 1 and I know un. Instead of un plus 1, I just subbed this in. Instead of un, I subbed in this. Once again, on both sides, and in every term there's a 2 to the power of n, which means I can divide both sides by 2 to the power of n and they're just gone. I just multiply out the right hand side, I get 3n minus 60. All we need to do then is move all our n's to one side, numbers to the other side, and I ended up working out that if this is true, then n has to be less than 22. In the question it said n has to be greater than or equal to 0. So to get the full marks here, you have to say that n is greater than or equal to 0, but less than 22. Those are the values of n. If n is anything in between those, then this statement will be true. Question 14 part A looked quite intimidating, but it was actually quite straightforward. You were given a geometric series, and the first term is 1, the second one is 3 over 2x plus 1, 3 over 2x plus 1 to be squared, and so on. And this is an infinite series. We're told that it's an infinite series, and you'll notice that there's dots going on to show that it never ends. This is an infinite geometric series. And I've been asked to get the sum of the infinite geometric series. You should remember from your sequences and series to get the sum of the sum to infinity of a geometric series is a over 1 minus or, where a is the first term in the geometric series and or is the common ratio. So obviously a, the first term in this series, is 1, and the common ratio of any geometric series can be calculated as any term divided by the previous term. So for example, the second term t2 divided by the first term t1. That's what I did in order to work out or. It's the second term, 3 over 2x plus 1 divided by 1. Obviously dividing by 1, I can actually allow to just ignore the 1, and I worked out that or, the common ratio, is 3 over 2x plus 1. Once I know a and I know or, I can just sub into the sum to infinity formula. It's a over 1 minus or becomes 1 over 1 minus 3 over 2x plus 1. What I want to do now is get a common denominator on the bottom of the fraction. Get a common denominator for 1 minus 3 over 2x plus 1. So in order to do that, I have to view this as 1 over 1. Clearly the common denominator for these two fractions is 2x plus 1. And I have to ask myself, how many times will the bottom of the first fraction divide into the common denominator? 1 divides into 2x plus 1, 2x plus 1 times. So it's 2x plus 1 times the top of the fraction, which leaves me with 2x plus 1. And then I've got a minus in between them, and the bottom of this fraction divides into the common denominator once, so I'm just left with a minus 3. If I simplify that down, I get 2x plus 1 minus 3 is 2x minus 2. Now, we've come across this once or twice already. We do not want to have more than one fraction line. So 1 divided by this fraction, instead of that, I want to get the reciprocal of the fraction and multiply. 1 divided by that is the same as 1 multiplied by the reciprocal. The reciprocal of 2x minus 2 over 2x plus 1 is if you just flip the fraction and get 2x plus 1 over 2x minus 2. Obviously 1 multiplied by that, the 1 has no impact on it, and I'm just left with 2x plus 1 divided by 2x minus 2. And that's your final answer for the sum to infinity of this geometric series. Okay, in question 14 part B, we were told that u1, we were given another series, and u1 plus u2 plus u3, the whole way up to un, is calculated as n times n plus 1. So that I've been told that if you add up a certain number of terms in this series, they'll add up to n times n plus 1. We've come across things very similar to this in induction, although this isn't an induction question. U1 is basically term number 1. U2 is term number 2. U3 is term number 3. And if I just kept on adding up all of these terms, the one at the end here is term n, or Tn. It's what we refer to usually as the general term. And I know that if I added up all of these terms, it would give me the sum of all of the terms Sn. So Sn, the sum of these terms, is calculated as n times n plus 1. So what I need to do here is I need to first of all work out what the first few terms are. I can relatively easily work out the first few terms because I know what the sum, I know what Sn is. So if I wanted to work out what the sum of the first 1 terms is, I would just sub in 1. If I sub in 1 into this, that will tell me what the first 1 term adds up to. So if I just sub that in, I'll get 1 times 1 plus 1, and obviously if you simplify that down, you're going to get 2. The first term, S1, adds up to 2. Obviously that just means that the first term is actually a 2. So I can say that U1, the first term in this scenario, must be 2. Now I want to continue on and see if I can work out what U2 is. now I'm going to see what would I get if I subbed in 2. I want to know if the sum of these terms is n times n plus 1. I want to know what the sum of the first 2 terms is. If I sub 2 into this, it'll tell me what the first 2 terms add up to. So in this case, S2 would be 2 times 2 plus 1. 2 plus 1 is 3, multiplied by 2 gives me 6. That tells me that the first 2 terms add up to 6. If the first 2 terms add up to 6, and I know that the first term is a 2, then 6 minus 2 tells me that the second term is 4. Now I know the first term is 2, the second term is 4, because the first 2 terms add up to 6. So that's fine. I can continue on now and I can work out what the third term is. In order to work out the third term, I'm going to hone in on S3. S3, if I subbed into this, will tell me what the sum of the first 3 terms is. So in this case, instead of an n, I can just sub in a 3. It becomes 3 times 3 plus 1. 3 plus 1 is 4, multiplied by 3 gives me 12. That tells me that the first 3 terms add up to 12. The first term is 2 and the second one is 4, that adds up to 6. 12 minus 6 tells me that the third term must be a 6. So I know that this is now 2 plus 4 plus 6. Now I can see that there's a trend. 2 plus 4 plus 6 plus 8 plus 10. If I continued on, it's just going to keep on going up in 2s. So now I can deduce that this is actually just an arithmetic sequence. I now have an arithmetic sequence, and I need to express un in terms of n. To get un in terms of n, then that just means I need to find the general formula. I need to find Tn, the general formula for this arithmetic sequence. Now this is going to be incredibly straightforward. If you go to the arithmetic sequences and series page in your maths tables, it tells you that Tn, the general formula for an arithmetic sequence, is a plus n minus 1 times d, where a is the first term and d is the common difference. In this case, a, the first term, is clearly just 2, and d, the common difference, is also 2. Once I know a and I know d, I can sub in and I'll be able to get the general formula for this arithmetic sequence in terms of n. So Tn in this case would be a, which is 2, plus n minus 1 times 2. And if I simplify that, it's just going to be 2, and then 2 multiplied by n gives me 2n, 2 multiplied by minus 2 gives me minus 2. So plus 2 and minus 2 cancel out, so I just work out that the general formula for this sequence is just 2 multiplied by n. And that makes a lot of sense. If I subbed in 1, 2 by 1 gives me 2. If I subbed in 2, 2 by 2 gives me 4. 2 by 3 gives me 6, 2 by 4 gives me 8, 2 by 5 gives me 10. So I know that the general formula for this sequence is just 2n. And in the way this question was worded, they're calling, instead of using Tn, they're using un. They're calling the general formula un. So the answer that you needed for this question was that un in terms of n, un is just 2 times n. Okay, in B part 2, we're given an expression that has un plus 1, un plus 2, and un plus 3 in it. So before we even worry about the expression, we should work out what each of these are. In the question, in B part 1, I've worked out that un, the general formula for this sequence, is 2 times n. So to work out un plus 1, instead of an n, I just sub in n plus 1. Un plus 1 must be 2n plus 2. Un plus 2 must be 2n plus 4. And un plus 3 must be 2n plus 6. Now that I've worked out each of those, I should be able to now prove what they're asking me to prove. Okay, so now that we've worked out un plus 1, un plus 2, and un plus 3, we can look at what they've asked us. They've asked us to prove that un plus 3 to be squared minus un plus 1 to be squared minus, so all of that's in brackets, and then we subtract un plus 2 to be squared minus un to be squared. So all I did was sub in. Un plus 3 is 2n plus 6, un plus 1 is 2n plus 2. Un plus 2 is 2n plus 4, and un is 2n. If I multiply 2n plus 6 by itself, I get 4n squared plus 24n plus 36. There's then a minus in between them, and I square 2n plus 2 becomes 4n squared plus 8n plus 4. There's a minus between the two large brackets, and then I have to square 2n plus 4 by 2n plus 4, gives me 4n squared plus 16n plus 16. And there's a minus, and then I multiply 2n by 2n and I get 4n squared. Now there's loads of signs here, so you just have to be careful. Inside this bracket, I'm going to have 4n squared minus 4n squared. So they're going to cancel each other out. I'm going to have 24n minus 8n. 24n minus 8n gives me 16n. And I'm going to have 36 minus 4. 36 minus 4 is going to give me 32. So from the first bracket, all I get is 16n plus 32. Then there's a minus here, and I've got 4n squared minus 4n squared, which will cancel, and I'm left in the bracket with 16n minus 16. With a minus in front of that, minus by plus 16n becomes minus 16n, minus by minus 16 becomes plus 16. Then 16n and minus 16n will cancel. I get 32 and 16, and my final answer is 48. Okay, in question 14, part C, we were asked to prove that ax plus by to be squared is less than or equal to a squared plus b squared by x squared plus y squared. We were told that a, b, x, y were all elements of OR. Once again, this is like question 6 on the previous page. This is an abstract inequality. Ultimately, I need to end up with everything to be squared on one side, and I'll be able to say that any real number squared is greater than 0. What I've done here, I've just started it off. I've multiplied ax plus by by itself, and I've ended up with a squared x squared plus abxy plus abxy plus b squared y squared. I've multiplied out these brackets as well. I got a squared x squared plus a squared y squared plus b squared x squared plus b squared y squared. You should now recognize that there's an a squared x squared on both sides, and that there's a b squared y squared on both sides. The two terms that I have on the left are like terms, so I can add them together. If 1abxy plus 1abxy gives me 2abxy. And I have to prove that that is less than or equal to a squared y squared plus b squared x squared. Once again, you need to recognize that this is an abstract inequality. And what we always do in these questions is we move everything to one side and prove that it's greater than or equal to 0. So in this case, I'm going to subtract 2abxy from both sides. And I'm going to end up with 0 is less than or equal to a squared y squared minus 2abxy plus b squared x squared. Now, this is the bit that's really tricky. One of the things that you had to learn, or that I've told you to learn, and it came up in the last one of these that we did, is that if you have a squared plus 2ab plus b squared, if you have a squared minus 2ab plus b squared, I would expect you to recognize that that can be factorized as a minus b to be squared. A squared minus 2ab plus b squared is the same thing as a minus b to be squared. That's what you have to recognize here. That's what I have here, except that my a in this case is ay, and my b in this case is bx. Imagine if this was just ay minus bx. So ultimately, I can factorize this line, and I can say that it is ay minus bx to be squared. Now, I want you to, in order to figure that one out, I want you to look at what we have here. A minus b to be squared is the same thing as a squared minus 2ab plus b squared. Whatever you have here, if you square it, it should give you this term. So ay multiplied by itself would give me a squared y squared. Whatever you have here, if you square it, should give you the last term. Bx multiplied by bx will give me b squared x squared. And the term in the middle, well, because there's a minus here because there's a minus here. And the term in the middle is 2 times a times b. So the term in the middle has to be 2 times the first term times the second term. 2 multiplied by ay multiplied by bx would leave me with 2abxy. So that was, I think that last line was very, very tricky. You had to recognize when you got to this stage that what you have is actually ay minus bx to be squared. So the thing is about these questions is the last 2 or 3 lines is nearly always identical. So you know that you should have been on the lookout for that kind of thing. I can say that this is true. I know for a fact that this is true. And the reason that this is true is because any real number to be squared is always greater than or equal to 0. You have to mention that, and you can't say that anything squared is greater than or equal to 0, because you know from looking at complex numbers, sometimes when you square a complex number, you end up with a negative value. Okay, question 15 was a little bit more straightforward than the previous one. In this one, we're asked to solve 2x minus y equals root 8x plus 1. You needed to identify that the problem here is that there's a surd. And in order to eliminate the surd, you need to square both sides. So straight away, if we square the right hand side, we'll end up with 8x plus 1. And if you square the left-hand side, you end up with 4x squared minus 4x plus 1. You have an x squared, you have an x, and you've got a number, which means you've got a quadratic equation. So you move everything to one side and factorize. When I moved everything to one side, I ended up with 4x squared minus 12x equals 0. And we can factorize out what's common here. The term that's common to both of these is 4x. If I take 4x out of the first term, I'm left with 1x. 4x into minus 12x is minus 3. I then let each factor equal to 0. So I can say that 4x equals 0, which means x equals 0. Or I can say that x minus 3 equals 0, which means x equals 3. However, remember that if you're dealing with surds, you have to sub your answers into the original equation to investigate which one is true and which one is false. Okay, so when we sub these in, first of all, you sub in x equals 0. When I subbed in x equals 0, I ended up with minus 1 is equal to the square root of 1. Now, some of you might be scratching your head at how I've concluded this one. You are allowed to say that this, usually what we always say is that the square root of 1 is equal to plus 1. You are allowed to say that the square root of 1 is equal to plus or minus 1. If the question asks you to get two different answers, you are allowed to say that it's equal to plus or minus 1. But in a scenario where you're only trying to get one answer, you are not allowed to only say that the square root of 1 is equal to minus 1. You are not allowed to do that. You're only allowed to take it as plus or minus 1. If you're taking two possibilities, then mathematically you're allowed to take plus or minus 1. But if you're only taking one possibility, which is the case in this scenario, you cannot take only the minus. So minus 1 is not equal to plus 1, so that one is false. On the other hand, when we work through the other one, you end up with 5 equals 5. So the answer that was valid there was x equals 3. Okay, part B was a basic simultaneous equation. At this stage in the year, it is very important to just be revising over the easy stuff as well. I think students have a habit of honing in on the difficult stuff, but simultaneous equations come in an awful lot. They come up a lot, so it's important we revise this kind of thing. In this case, I decided to eliminate my x's. Now, you don't have to do it. You could have eliminated the y's or the z's, but I've decided to go with the x's. I've labelled my equations as A, B, and C. And what I decided to do first of all was to take B and C and to eliminate x. So if there's a 2x in front of B, then I want to have a minus 2x in front of C. So I decided to multiply C by minus 2. And my C became minus 2x minus 6y minus 4z equals minus 14. In that case, the x's will cancel and I'll get minus 5y minus 7z equals minus 23. And I'm labelling this as equation D. Then I had to go back and take two other equations and eliminate x again. So this time I decided to take equation A and equation C. Because there was a plus 3x in front of A, I want a minus 3x in front of C, which means I needed to multiply C by minus 3. And I got minus 3x minus 9y minus 6z equals minus 21. The x's will cancel and I end up with minus 4y minus 7z equals minus 24. And I've labelled this as my fifth equation, equation E. If I now look at equation D and equation E, I have two equations and two unknowns, which means I can solve this by doing a simultaneous equation. Once I find y and I find z, I can sub back into one of these original equations and find x. So now that I have equation D and equation E, I decided to eliminate my z's because I have a minus 7z and a minus 7z. I decided to multiply the bottom line by minus 1 so that I would have a minus 7z and a plus 7z. So I changed all the signs of E and I end up with minus 5y plus 4y, which is minus 1y, minus 23 plus 24, which is plus 1. If minus y equals plus 1, I change my signs and I work out that plus 1 equals minus y. If minus y is equal to plus 1, I changed my signs and I ended up with plus y is equal to minus 1. Now that I know y, I can sub back into either D or E in order to find the value of z. I decided to sub into D. Everywhere there was a y, I subbed in a minus 1 and I ended up with z equal to 4. Now that I know y and I know z, I can sub back into A, B or C to find the value of x. So I decided to sub into A. Everywhere there's a y, I subbed in a minus 1 and everywhere there was a z, I subbed in a 4 and I ended up with x equals 2. So those simultaneous equations are straightforward enough, but it's incredibly easy to make a silly sign error somewhere, or it's just don't take for granted that you're going to get full marks in those ones. They do require a bit of practice over the next few months. Okay, the last thing in this revision handout was long division. I told you that x squared plus ax plus b is a factor of this polynomial. And you've been given two random looking expressions to prove. At the start of a question like this, don't worry about those at all. If you've been told that this is a factor of this polynomial, that means you can divide x squared plus ax plus b evenly into this. So I'm going to divide this quadratic into this cubic, and my remainder is going to be in terms of or, q, s, a and b. But I know that the remainder is equal to 0 because they've told me that this is a factor, so whatever the remainder is, I can let it equal to 0. And when I do that, hopefully I'll be able to prove the two things that they're asking me to prove. So we're just going to do long division the same ways we've been doing it for the last few years. We're going to divide x squared into x cubed. X squared into x cubed goes 1x times. Then we're going to multiply x by these three terms. X by x squared will give me x cubed. X by ax will give me ax squared. And x multiplied by b will give me bx. The third step in long division is to subtract. And in order to subtract, you need to change your signs. So all of these are going to become minuses. In that case, my x cubed will cancel. And here is where things are going to change. I have qx squared minus ax squared. These are not like terms. When you get to the point where you have things that aren't like terms, you should do it out in your rough work. I have qx squared minus ax squared. The way that I want to write this down here is I want to factorize out what's common. The term that is common is x squared. So I could write qx squared minus ax squared as q minus a times x squared. And life will be made a lot easier for us if we write it like that. I can follow the same logic here with the coefficients of x. I have or x on the top minus bx on the bottom. If I factorize out x, I'm left with or minus b times x. So I can just write this as or minus b times x. The fourth step in long division is to take down the last term, which in this case is a plus s. And now I just want to start my process all over again. I want to divide x squared into q minus a times x squared. X squared into this term, well, the x squared will cancel with itself and I'll just be left with q minus a. Now I need to multiply q minus a by these three terms. Q minus a multiplied by x squared is just q minus a times x squared. Q minus a multiplied by ax. In this case, you're better off not to bother multiplying it out, just write it down. Q minus a ax, it's the handiest way to write it. And then you're going to multiply q minus a by b, and when you do that, you're just going to write it as q minus a times b. And at this stage now, I'm getting towards my remainder. The third step in long division is I need to change my signs. So this becomes a minus, this becomes a minus, and this becomes a minus. You cancel your x squareds, and now we're at our remainder. I know I'm at my remainder because I've got no more terms to take down. There's nothing left. So remember that you get two separate remainders. The first remainders are the coefficients of x. The second remainder are the terms on their own, the constants at the end. The coefficient of x on the top line is or minus b. Remember that, and it's or minus b times x. And the coefficient of x on the bottom, what I have is minus q minus a times ax. That's my first remainder. Your second remainder is the constant on the top, which is s, minus the constants on the bottom, which are q minus a times b. Now, this question told me that this quadratic is a factor of this polynomial. In other words, it's telling me that the remainder is equal to 0. So that tells me that each of these is equal to 0. So I can let the first remainder equal to 0x. I can let the second remainder equal to 0. The reason I'm letting the first remainder equal to 0x is because, in fact, we don't need the x's at all. It's just the coefficients of x that add up to 0. Basically, if that's a 6x, this is minus 6x. If that's 10x, this is minus 10x. The 10 and the minus 10 cancel each other out. The fact that there's x's there, it doesn't matter for this case. Now that I have these two expressions, I'll be able to prove what I was asked to prove. The first thing I was asked to prove was basically I just need to isolate my or minus b. the first expression I was given had or minus b on its own. So all I need to do is take this term and move it to the right hand side. So I leave or minus b on its own on the left, and to bring this term to the right hand side I'm going to add a times q minus a to both sides. Basically it just means you change the sign of that term and you're left with or minus b equals a times q minus a. So that's the first thing that you were asked to prove. The second thing you were asked to prove was you were asked to get s on its own. If I tried to isolate s here, basically I'm just going to bring that term to the other side. In other words, I'm going to add b times q minus a to both sides, and I realize that s is equal to b times q minus a. So once you do the long division in those questions, in general, to work out the expressions you're asked to prove, it's usually easy enough. Now, so that brings us to the end of that revision sheet. There was a lot of things that I'm sure you found very difficult in that, but the more revision that we do over the next few months, the more it just reminds you of things, because there's a lot of little bits and pieces that I'm sure if we leave you to revision yourself, you'll forget about them.